Okay, thank you, Miguel. And I'd like to thank Olympia for inviting me. And I'd like to thank Olympia even more for inviting all these other speakers, because I've really learned a lot and I've really enjoyed the talks, and I really look forward to tomorrow's talks. And I'd also like to thank everyone else involved in organizing this conference and making it happen. Okay, I'm going to, when I first sent Olympia my title and abstract, I was really little worried that it wasn't going to really fit into the theme of the conference, because even though I am going to be talking about locality, I don't actually have much to say about identity and indistinguishability. But interestingly enough, several of the speakers have already touched on things that I want to talk about, so I think we're good. Okay, let me just start off with a sort of overview, rough taxonomy of approaches to the measurement problem. And when I categorize these, I like to think about Bell's dictum at the beginning of his paper, Are There Quantum Jumps?, where he says, the wave function as given by the Schrödinger equation either isn't everything or it's not right. And by the way, today is John Bell's birthday. He would have been 89 today. And that gives us a rough taxonomy of approaches to the measurement problem. Because there's those who say, well, yeah, what we have is the Schrödinger evolution, unitary evolution all the time, but there's something else. These are like what they call extra beables theories. So that includes Bohmian interpretations, hidden variables theories, and various modal interpretations. And then there are those that say, well, actually the Schrödinger evolution isn't quite right. And for those of you who aren't familiar with these theories, the idea is to introduce a stochastic, non-unitary evolution that inappropriate circumstances leads to something like the textbook collapse of the wave function. And the best known version of this is the GRW theory, Geraghty, Rimini, and Weber. There's a continuous version of it called continuous spontaneous localization, CSL. And there's various generalizations of these things to relativistic theories. And basically what they do is they pick some observable such that superpositions of distinct values of that observable will tend to get suppressed, and you'll get collapsed towards eigenstates of those observables. And then there are those who deny both horns of Bell's dilemma. So the Everettians in particular say, well, actually, the quantum state is everything, and it evolves unitarily at all the time. So Everettian relative states, I think, even though Carlo Rovelli isn't a realist about the wave function, I'm going to put him here. Probably, I think I'd want to put the sort of relational modal interpretations that Dennis is advocating for the purposes of talk in that kind of thing. Okay. And one question that's long interested me in connection with these things is how do they stand when it comes to compatibility with relativistic causal structure? And what I mean by relativistic causal structure is if I give a region of relativistic causal structure, as I mean it, says if I have a region of space-time, then the things that can influence things in that region of space-time are confined to the past light cone. In particular, a difference between a relativistic space-time and Galilean space-time, the pre-relativistic space-time, is the latter has a distinguished relation of distance simultaneity. So I'll say that if you've got causal relations outside the past light cone, that's not a respecting relativistic causality in the way I mean it. And that includes theories that have causation forwards and backwards, because if you can have forward and backward correlation on any time-like line, then every part of space-time is in the causal domain of every other part of the space-time, right? I'm not concerned with the question about whether that causal structure is dynamic or not, because Nino mentioned that there are possibilities where you start with everything in a Minkowski spacetime, but you introduce a distinguished foliation to hang the dynamics on via Lorentz invariance equations. So that's one that has a distinguished relation. And there are arguments that these sorts of hidden variables theories, as long as they're local hidden variables theory, I mean, as long as the stuff that's added is local beables, right? I don't mean local hidden variables theory in the sense of having local dynamics. There's an argument that they actually do need to have a relation of distance simultaneity, and I guess want to make clear the relation between these two papers. This latter paper was mentioned by Dennis yesterday. So the basic argument is in a paper by Karin Berndl and collaborators, including Nino Zanghi, and they consider theories in which the extra beable is position, trajectory theories. And I found myself wondering, well, does this apply to, can the argument be extended to the sorts of more general modal interpretations considered by Jeff Boob in his book, Interpreting the Quantum World? And I thought about it for a while, and I realized that actually the argument goes fairly straightforwardly over into those kinds of things too, and that's my Foundations of Physics paper, 2002, that is mentioned. Dynamical collapse theories. I mentioned the paper, Are There Quantum Jumps, at the very beginning by Bell. That was written shortly after Bell learned of the GRW theory. And being Bell, one of his first questions in his mind was, well, how does this fare with respect to relativistic causal structure? Does this require a distant relation, a distinguished relation of distance simultaneity? And even though it's formulated in terms of non-relativistic quantum mechanics, he was able to ask the question in that framework by considering particles that aren't interacting with each other in a distance apart. And the answer is the theory doesn't care what the temporal order of distant events is. And he said, this takes away the ground of my fear that there can't be an interpretation of quantum mechanics that's compatible with serious Lorentz invariance. And basically, we now have some kinds of relativistic collapse theories on the table, and indeed, they don't require anything except the light cone causal structure in order to work. But I guess say something about how they do work is that because it's a condition that Bell in one of his later papers called local causality, which is that conditioning on events in the past light cone, if I have two events, if I have events of space-like separation, I have probabilities here conditional on the past light cone of region A. The probabilities outside space-like separation are independent. They violate that condition. So they have these theories have built into the stochastic dynamics irreducible correlations between events of space-like separation. But if I say there's a correlation, that doesn't require me to say one of those happens first and the other one happens second. The theory doesn't care about the temporal order. The theory does not need a distinguished relation of distance simultaneity for its dynamics. So that's what I mean when I say that these kinds of theories are fine. They can respect relativistic causality. If you're interested, I argue that in more detail in my contribution to this book that came out last year, edited by Mary Bell and Sean Gao. And I think for the Everettian theories, the same is true. They don't particularly need any distance allowance. There's no problem with that. Yeah.
You cannot put it the same thing. It's obvious in the last case. You have to make all kind of exercises and definition, trying to say that there is kind of similar in a second.
Okay, so to Lev, it's obvious, right? The last one. Okay, but I think we agreed on the check mark there. Okay, all right. Now, what is the issue now with these dynamical collapse theories? Well, one thing that is an issue, one thing that is a problem, I think, is what kind of local beables these theories might support. Because remember, the motivation of those kinds of theories was all there is the quantum state, and it just evolves non-unitarily. And Lev was, I was just talking with Lev just before that. He goes, the wave function, that's a local beable? What? Yeah, right. So if you're saying all there is the quantum state, it's not obvious that there's any local beables at all in your theory. And what I mean by a local beable, do I say, I hope I say this on the slide here. Yeah. Oops. Maybe it's on the next slide. Okay, well, I didn't actually say what I mean is, what I mean is that, as Bell defines it, it's something, some matter of fact, some property you can associate with a bounded region of space-time. And it has to be, it's meant to be sort of an intrinsic property of that region of space-time. So for example, if I have an extended system of masses, I might say, well, the center of mass of that extended system is right here. It's in this little region. But obviously, the fact that the center of mass is in that region is not a fact about that region. It's a fact about a distribution that goes way outside the region. So a local beable for this room is supposed to be something, some beable, some property we associate with the stuff in the room that is not an implicit reference to stuff outside the room. That's the basic idea. And you might say, okay, well, who needs them? Maybe we can do without them. We're sophisticated people. We've decided that the world is quantum. We don't try to impose our classical intuitions on the world. Who needs them? Well, I claim you do, and that's everybody. Yeah. And the reason is that the only reason we're talking about quantum mechanics in the first place is that we have a considerable body of experimental evidence that quantum mechanics is getting something right. And when experimentalists go in the lab, they're setting stuff up in the lab, they're manipulating stuff in the lab, they're getting results in the lab, and those better be local beables, else it's really hard to make sense of doing an experiment and getting an outcome. Okay. So the evidential base for our physical theorizing is in terms of local beables. If I say, okay, we're past that, I'm a sophisticated quantum person now, I'm going to give that up. Well, I sort of swept the rug out from under my reason for being a sophisticated quantum person because I've lost, apparently, any way of making sense of the experimental evidence for the theory. Okay, so it runs the risk of undermining its own evidential base. Okay, all right. Okay, here's the characterization of local beables. This should have been on the previous slide. Yeah, so this is a quote from Bell in his paper, Theory of Local Beables. Those which, unlike, for example, the tonal energy, can be assigned to some bounded space-time region. And as I said, I want to add, they should be those which be right intrinsic to the bounded space-time region they're assigned. And for you non-philosophers, all that means is not a relation to something else besides it, not an implicit reference to something besides it. So yeah. Okay, so I'm going to ask a seemingly naive question. What's it take to be a local beable? What's it take to be the sort of thing we take our experimental apparatus to be? Our evidential talk is couched in terms of sort of ordinary three-dimensional objects we deal with every day. Philosopher G.E. Moore, in his paper, A Proof of External World, calls them things to be met with in space. So what are those? What does it take for a theory to represent things to be met with in space? Interestingly enough, that was a question that was addressed at the very beginning of modern physics by Newton, even before he wrote the Principia. There's this manuscript that went unpublished and before the 20th century. Actually, let me just set this up. There's a manuscript that went unpublished before the 20th century called On the Gravitation and Equilibrium of Fluids. It's got this long Latin title. It's familiarly known as De Grav. The manuscript isn't dated, but scholars think it is sometime before the Principia. How long before the Principia, there's a matter of debate. But what it seems to be is Newton's break with Cartesianism. And in this passage I'm about to quote, he's criticizing the Cartesian notion of what it is to be a body, a thing to be met with in space. Because according to Descartes, the essence of a body is extension, occupying a certain region of space. So for Descartes, there's fundamentally two kinds of things in the world. There's res extensa, extended things, and res cogitans, thinking things. The essence of a body is extension. And what Newton is saying is, well, look, that can't be all there is. Because there's lots of extended regions of space in this room, only some of which are occupied by solid objects. And he's asking himself, well, what's the difference between extension that's occupied by a solid object and an extension is not? And here's what he says. Let us then feign empty spaces scattered throughout the world, some one of which, defined by certain limits, by the divine power becomes impervious to bodies. And it is manifest ex hypothesis that this will oppose the motions of bodies and perhaps reflect them, and will assume all the properties of a corporeal particle except it will be immobile. We further imagine that impenetrability not conserved always in the same part of space, but able to be transferred hither and thither according to certain laws, yet so that the quantity and shape of that impenetrable space are not changed. There will be no property of bodies that do not belong to this. It will be figurate, tangible and mobile, able to reflect and be reflected in any combination of things, will be no less constitute a part than any corpuscle. And what he's saying there is, what it takes to, and he later says that actually, if all our bodies were just these sorts of regions of space, nothing would be different. What it takes to be a solid body, the difference between a region of space in which there's a table and a region of space in which there isn't a table, is that there are certain dynamical properties associated with that region of space. Right. Yeah, so to be a thing to be met in space is to occupy a certain place within a network of dynamical and causal relations. And I guess I'll point out, Newton imagined a space with certain definite limits that had these properties, but clearly that's not necessary. It could be that, say, this table exerts negligible repulsive effect until I get really close to it, and then it goes. Then the repulsive effect goes up very quickly, but there's no precise boundary to the table, right? Things like that, and things can be permeable to other things, and not to others. Things can reflect some wavelengths of light and pass others through. But okay, and he says that, unlike, say, the Aristotelians, we don't have to assume some kind of unintelligible substance without properties in which these dynamical properties inhere. Okay, all right. So I want you to bear that in mind, that if we start looking for local beables, tables and chairs and things, that's what we're going to need from any physical theory that has them in them. Okay, now let's talk about quantum theory. What do you do when you construct a quantum theory? Well, you start with some system that you want to study. It could be a hydrogen atom. It could be a molecule. It could be something big and complicated. And you identify the degrees of freedom of that system that you want to study, and the dynamical variables, and you associate to them self-adjoint operators, and you impose the appropriate commutation relations on them. And then, so you've got associated your system a certain algebra of operators. And then what a quantum state is assignment of expectation values to these operators, linear, positive linear functionals on these things. And for certain kinds of theories, that the state can be represented by a wave function on a configuration space, for example. And as Nino emphasized, the configurations we're talking about are for n particles. They're n tuples of points in space. They have an intrinsic relation to three-dimensional physical space. It's not an abstract 3n-dimensional space. Right. So, all right. And how do we understand this? How do we get to attribute properties in a quantum theory to objects? Well, from the very beginning, in Dirac's textbook for quantum mechanics in the first edition, and in von Neumann's mathematical foundations of quantum mechanics, it's explicit that if system is an eigenstate with eigenvalue A, of the operator corresponding to a certain dynamical variable, then we say it has that property. So if an atom is in a certain energy eigenstate, we say that atom in certain energy state, we say that atom has that energy. If the position of that atom were an eigenstate of being in a certain box, we would say, okay, there's a certain amount of energy in that box. Notice I switched to the subjunctive there. Yeah, right. So, right, yeah. So now what's often, I think, misleadingly called the measurement problem, and which Giancarlo Ghirardi calls the problem of macro objectification, is that if you think your measurement apparatus in this table, in this chair, and everything can be treated by quantum mechanics, and as James pointed out, that is a substantive assumption. But if, in fact, they can be treated by quantum mechanics, even if they started out in an eigenstate of being in, of various local beables and having nice properties, very quickly they would evolve into states that are not such eigenstates. And if we take that a system has a certain dynamical property only if it's in the corresponding eigenstate, then okay, you know what? There's nothing in this room, because none of the atoms can possibly be in eigenstates of being in this room. They can have, their wave functions are going to have tails. They can be very, very small, but they're not going to be zero outside the room. Right. Okay. Yeah, and so even if at some moment they did have, were in eigensort of properties of properties we tend to think they have, they'd quickly evolve to states in which they have no determinate properties. And the particularly vivid examples of that are, of course, Schrodinger's cat, or what happens in a typical measurement where the apparatus, if it can be treated quantumly, and if the evolution is unitary at all times, ends up in being a superposition of reading different things. Okay. All right. So this is the reason why first von Neumann and then Dirac introduced the collapse postulate. And that's basically just saying, well, no, things don't always evolve unitarily. you do an experiment, and after the experiment, you get an eigenstate of whatever it is that you observe. We call this the naive collapse postulate. Okay. And what I want to claim is, if that worked, if the dynamical collapse theories that Girardi and Riemann and Weber and other people constructed actually did give us that naive collapse postulate, if actually did give us states that are eigenstates of local beables, there would be no problem of the ontology for collapse theories. Things would indeed have local. All it takes is to be for there to be a table there is for this region of space have the right dynamical properties associated with it. Von Newton. Okay. But this can't be. For the GRW theory, for those of you who know it, it's a theory for non-relativistic quantum mechanics. And basically, every particle has a certain probability per unit time of undergoing a collapse, which means its wave function gets multiplied by a certain narrow Gaussian. Gaussians have tails. The GRW in their paper addressed the question of why they didn't choose a collapse function that had compact support, and the answer is, well, that wouldn't get rid of the tails, because even though at a certain moment something has a wave function has compact support, unitary evolution has it spread out everywhere immediately. Right? All right. So if we have, if we take what a quantum state is telling us is things have the properties that they're eigenstates of and no others, then there's a problem of making sense of these collapse theories, of giving us things to be met with in space. And this is often called the problem of tails, and I claim that the problems associated with ontology for collapse theories just is the problem of tails. Okay. Now, obviously, the people who first wrote down these collapse theories were aware of this, and they wrote things addressing the problem of how to interpret it. And if you look in the literature, the first option that Girardi and co-workers opted for was, well, okay, we can't precisely localize things in bounded regions, but we can make the tails really small. So my collapse theory would say, okay, the table, none of the atoms in the table are eigenstates of being in this room, but they're darn close to being eigenstates, absurdly close, with higher precision than anyone ever gets in science. And so the idea is close enough is good enough. Being close to an eigenstate of appropriate observables suffices. Eventually, Girardi became dissatisfied with that approach. And his current view is actually no, in a collapse theory, to make sense of it, has to be supplemented by extra ontology, a mass density that is something over and above the quantum state. Okay, so here's just a quote from Giancarlo Renatagrassi and Philip Pearl from 1990. We think the appropriate attitude, and this is appropriate attitude towards interpreting dynamical collapse theories, when considering a local observable A with its associated support, we say an individual system has an objective property A being an eigenvalue of A, only when the mean value of the associated projector is extremely close to 1. When evaluated on all space-like hypersurfaces containing the support of A. So they're already thinking of this in a relativistic context. And I guess that might be not entirely clear, but let me explain what that means. So if I've got a region, let that blue region be A, some region A. I can consider various space-like hypersurfaces passing through it. There's one. There's another one. And I can have quantum states associated with each of those hypersurfaces. The quantum state yields probabilities for outcomes of experiments to the future, conditional on everything that happens to the past of the hypersurface. Now, it's easy to show that if the evolution, sorry, do I have a pointer? That one? Okay, if the evolution between these two hypersurfaces is unitary, then the reduced state of that region is the same no matter which one of these space-like hypersurfaces space-like hypersurfaces that I take. And the reason for that is stuff associated with this commutes with the Hamiltonian that's going to be driving that evolution. However, on a collapse theory, and these little stars are supposed to be places where a collapse occurs. So if the evolution is non-unitary, then the reduced state of that region won't in general be the same for all of those hypersurfaces. And it's easy to see. I mean, suppose, for example, it's an EPR pair initially in the singlet state, and here's Bob looking at his spin 1/2 particle, and Alice is doing an experiment over here. If she does an experiment, so before her experiment, if she does, if this is the state before her experiment, the state is the singlet state. On this, the reduced state of Bob's qubit is just the totally mixed state. She does an experiment. Her qubit collapses to whatever the result of the experiment, and say spin up in the z direction, and then on this hypersurface, on this hypersurface, the reduced state is going to be spin z minus for Bob's qubit. And so what Girardi et al. Are saying, well, look, they don't quite so explicitly. A local beable, as I said, is supposed to be an intrinsic property in this room. It's supposed to be an intrinsic property, not a relation to something way outside it, right? And so what's going to count? Well, all of these things are, the reduced state derived from states on all these hypersurfaces are going to have that relational character. But as you go closer and closer to the past light cone, eventually there's a limiting state which incorporates only past collapses in the past light cone, and those are the ones that are really in the past of that region. So the state that they're going to use to evaluate their beables is that limiting past light cone state. So that's what this means. When evaluated on all space-like hypersurfaces containing the support of A, it's basically roughly equivalent to that's basically equivalent to saying you're considering this past light cone state. And if you're worried that the light cone isn't a space-like hypersurface, just take the limit as they go. Okay. Yeah.
If you cut this place by 2,
yes.
then you get some disagreement, yes?
Okay. Yeah. So suppose I've got two regions, right? Yeah. 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 Yeah.
And then
Right.
you cut by left side and right side, and you'll see different. And this star on the left will not be part of the right side.
Right. Yeah. That's absolutely right. Right. And so what you can do is you can say, well, if I really want to know what's here, then just shrink down to a point. Yeah. But that's absolutely right. What's that?
Helmholtz.
Yeah, right, yeah. Yes.
That also mean that the beables of the region are the sum of the beables of the regions to some tabulation.
That is correct. That is not going to be true. Yeah. Yeah. So yeah. So and that's kind of obvious because if I have two space-like separated regions, and I say where are the beables for this region, where are the beables of this region, there might be more beables for the combined region than there is the sum of the two things. That's absolutely correct. Yeah. So yes, it's not going to be satisfied this condition that you can just to find the beables in an extended region, you can't just look at all the subregions and add them up. Non-separability, yes, absolutely. Okay, all right. And so I've said that already. All right. What I'm going to call the intrinsic state of R incorporates only collapse regions in the past light cone of R, and it's the limit of states on hypersurfaces that approach the last point. Okay. So here's the proposal. So we've already seen the proposal from Gherardi and collaborators in the 1990s. Close to an eigenstate is good enough, and in a relativistic concept, the state to which that refers is going to be the past light cone state. Now, what Gherardi says these days is what we're going to do is actually define a mass energy density as the expectation value of the corresponding operators evaluated on the past light cone. So again, it's an intrinsic kind of thing. And take this to be real, consider its ontology above and beyond the quantum state. So this fits very well with the talk of primitive ontology, and Gherardi is very much was I think influenced by the people who introduced this talk of primitive ontology about this, right? And so it's a very good fit with this sort of primitive ontology framework. Okay, I think when I read that paper and other papers that talk about primitive ontology, I find myself agreeing with a lot of what people say, but there's also sort of a nagging worry. And my worry is that when you're trying to talk this way, and the basic idea is, well, we already heard it from Mikhail's talk this morning. Basic idea is that there's certain kinds of ontology, stuff that the theory is in the first instance about, and then any other ontology is introduced to provide dynamics for that stuff. And I think that's a temptation. I mean, so I have a great deal of respect for the people who write these, the people cited, including some people in this room. I think there's a temptation to fall into thinking that, well, there's a sort of two-step process that we can postulate some kind of dynamically inert primitive ontology and then endow it with dynamical properties. And my worry is that I don't even know what to make, if there's dynamically inert stuff there, I don't even know what sense to make of even talking about it as stuff, right? If you tell me there's a dynamically inert particle located here, well, what's the difference? If the region of space where the particle is located has no dynamical properties to distinguish it from any other region of space, I actually don't know what it means to say there's a particle located there. To my mind, I've never found the distinction between primitive and non-primitive ontology of a theory to be actually particularly clear. Like when I think of classical electromagnetism, where there's charges and fields, the people who developed that theory thought that they both had to be regarded as real. Maxwell's argument for taking the fields to be real is they carry energy and momentum. You could, if you wanted to, say, though the charges and charge densities are the primitive ontology and the fields are the sophisticated ontology. What's the opposite? The non-primitive ontology. Or you could do it the other way around. You could say the electromagnetic fields are the primitive ontology and the charges role is to be sources of those fields. But there doesn't seem, in a lot of cases, to be a natural distinction. Anyways, even if a principal distinction can be made, I just want to urge everybody to avoid falling to this temptation to think, okay, we can just postulate dynamically inert stuff and then endow with properties. To be stuff is to have a relationship. It's a certain relation, certain place in a nexus of causal relations. And I think Newton was absolutely right about that. What's that?
Space. You have different, so you have the space as your basic structure.
Yeah, I mean, Newton was presuming it's a kind of empty space as a background, but right, yeah. Yeah, but so if same thing happens. I do think that to be something, to be stuff, is to play some kind of a causal role. Yeah. Right. Good point. Right. Okay. And actually, I found a nice quote from von Helmholtz. He says that when we start to do a physical theory, we make a couple of abstractions. We abstract from matter, everything except its place and its motion. And so matter in itself can partake of one change only, a change which has reference to space, that is motion. And then we also abstract and consider the dynamical laws in isolation. But then he says, we should always remember the two of them always go together. Natural objects are not, however, thus passive. A mass of pure matter, namely, something that had no properties except place that could change, would, as far as we in nature are concerned, be a nullity, inasmuch as no action could be wrought by it, either upon our organs, senses, or the remaining portion of nature. So, I think that both Newton and Helmholtz Helmholtz is here reflecting on the structure of classical mechanics, and I think he's right about that. Okay, how much time do we have?
10 minutes. No, 10 minutes for your talk.
Okay, all right.
In total,
okay.
we have 20 minutes.
So,
maximum 10.
Okay, so if we think about what it takes to be a solid body, bare mass density isn't enough. We have to think of the charge densities. It's really, most of what's, those properties that I mentioned with this table have to do with its electromagnetic properties. And there's no grounds for regarding the charge densities as any less real than the things. Okay, so I want to talk about the second proposal, the mass density as primitive ontology. And using an example from a paper by Ghirardi and collaborators who were actually arguing for option 1, the close enough is good enough. So consider there's a state in which there's a superposition of being a mass in location A and location B. Okay, so a mass M, and let's say it's an equally weighted superposition. And so we can calculate that mass density, the expectation value, and it's going to be half M in A and half M in B. Right. However, that stuff that according to option 2 is the stuff that's really there has no dynamical significance whatsoever. If I shoot another test particle between them, it doesn't act as, and say let it be attracted gravitationally. It doesn't act as if there's half M here and oops. It doesn't act as if there's half M there and half M there and go straight through. What it does is it acts as if there's a superposition of M there and a superposition of M there. And what you get is the state of that thing goes into a superposition of going this way as if M is in A and going that way and this M is B. So this stuff that on option 2 is regarded as the real ontology actually doesn't have any kind of dynamical properties at all. And what they say is only in the cases where that variance is negligible, only in cases where it's close to an eigenstate of the mass being here or close to an eigenstate of the mass here, do things actually respond to it in that ways? And so that's the argument as originally given for saying the proper way to think about these things is close enough is good enough. And that brings us back to option A. And I want to say actually that if you're going to make sense of dynamical collapse theories, the option 1, that's the way to do it. And I think that there's actually a principled way of saying that's right. Recall I argued earlier that if the naive collapse postulate worked, there'd be no problem of ontology. But what these dynamical collapse theories can do, they can't produce exact eigenstates of observables, but they cannot get awfully damn close. And I think it's actually a fairly general principle of interpreting physics that if your interpretation changes radically with very small changes of the state, there's something wrong because, for one thing, then we never know what to say because we only know the condition of anything within a certain amount of approximation. So if you accept that continuity principle that small changes in the quantum state correspond to small changes in physical meaning, it leads us naturally back to option 1 that close enough is good enough. And that's the position that Philip Pearl is still advocating. So as I said, Girardi has gone to option 2. I would like to urge philosophers to take seriously Philip's view. So in conclusion, and also, I don't see any particular reason for singling out one kind of stuff as the stuff is real. I can remember what I said, from Newton and Helmholtz. To be stuff, to be somewhere, is to be part of a nexus of causal relations. And okay, this table has certain masses associated with it, but its optical properties and its repulsion to my thing have to do with its electromagnetic properties. So there are no grounds for thinking of the charge density as having some kind of inferior status. So I would just say, and this is Philip Pearl's, is all observables. You should take if something's close enough to an eigenstate of any observable, then for all intents and purposes, that the observable has that definite value.
Even non-local observables?
Yes. Yeah, even non-local observables. But remember that the problem with collapse theories is there weren't apparently enough local observables, right? Okay. All right. Thank you.
Maybe I'm probably missing something. So I didn't understand that to get there to be something with like some determinate value or something that if we had eigenstates we would be okay. And I didn't get that part, so then I don't get close enough to an eigenstate.
Okay.
Okay. I mean, it seems like whether you have an object there, whether you have something, right? You're saying it depends on it's kind of there being something with certain dynamical features, and that's not something that you can tell just by like kind of what space it fills in at the time, or I mean by something like a synchronic state of something. So I guess I feel like this.
Okay. So so the issue is being in an eigenstate is a synchronic state, right?
Being in an eigenstate is a synchronic state. The shape of the shape of the wave function at a particular time is a synchronic state. And if you want objects, it seems like you need something that involves behavior over time. Yeah.
Yeah. Thank you. That's good.
Okay.
Yeah. So, and next time implicitly, right? And next time I give this talk, I'll make it explicit. is, yeah, part of what it is to be an eigenstate of something is to behave in a certain dynamical way. So I'm assuming, I'm assuming we've got a dynamics, whether it's unitary dynamics or the collapse dynamics there. And I mean, one of the arguments for the eigenstate-eigenvalue link is if something is prepared in an eigenstate of a certain observable, and then you measure that observable, and that, of course, is a dynamic interaction with the measuring apparatus, that's the result that you will get. So yes, I was sort of assuming that, yeah, to be in a certain quantum state is not, it carries with it the idea that it responds to certain things, responds to things in certain ways.
I guess maybe then I heard it, when you were saying like if the tails weren't there, right?
Yeah.
If the tails weren't there, things would be okay.
Yeah.
So you were saying things like
Yeah.
that. And so that, I mean, that seems to suggest that it's just a matter of the shape at a time.
Yeah, and what I really meant is if the tails weren't there, right? So, like, if I had a particle definitely located in this box with no tails, then an ideal particle detector would definitely say particle there. Now, as a matter of fact, the best we can do is close to 1, right? Right. So yeah. So yeah, thanks for that question. I am thinking of these things as dynamical properties. Yeah.
May I have a few comments? First, I like very much that you kind of promote the original collapse story and not all this new phenomena flash you didn't mention, which is maybe good. And this mass density, which I think there is no any reason whatsoever to call it any kind of ontology, because the wave function is already there. The mass density can be calculated and charge density can be calculated. So you have everything there, and so it's not needed. So the original, the ontology is a wave function. So this is great.
Good.
Now you say the tails are a problem, and I thought that the tail is a big problem, because I thought that if I have a quantum experiment in which the outcome A, I'm sitting in this chair, and outcome B, I'm sitting in that chair.
Right.
And then there is a GRW collapse, and they say, okay, there is a tail, very small tail, so there is me here with amplitude close to 1, and there is me there with amplitude close to 10 to the minus Google.
Yeah.
So forget about it. But for me, if there is a structure of me there, the number is not so important. Until I realized that there is me here alive,
right,
and there is a me there dead. And this, for me, kind of makes the problem of tails is very small. There is only one word in which the normal one, in all other one, I'm disintegrated because multiplying by tail looks like a flat tail, but it's very not flat tail, and all my molecules will be distorted very soon.
Yeah. So thank you. Because one thing that people used to say is these dynamical collapse theories are sort of many worlds in disguise, because you have a Lev, superposition of Lev here and Lev there, and the amplitude is very small. But as you pointed out, actually, terrible things happen to that other Lev. So there's some stuff there in that tail, right? So what the collapse theory would say is, yeah, there's some stuff there, very small amount of stuff there, but it ain't you, because it's the collapse doesn't just shrink the amplitude down. It's going to do all kinds of terrible stuff to you. Yeah.
Okay, my comment will be the opposite of Lev.
Okay. All right.
But I like it very much, your talk, because you were very clear. And I think you presented in a fair way both options, and of course. And both have some drawbacks. I mean, you show the drawbacks of option 1,
right,
of option, and also of option 2, I think. No, that's And so I wanted just to say something about some comments that were related to some proposal I made with my other friends, like in
Yes.
the common structure of... yeah, you said you can have a tendency to go to this splitting. Now you say step 1, step 2.
Right.
Okay, then you quoted a lot Newton, I quote Cauchy or Ampere. I mean, the modern understanding in the end of the 18th and the beginning of the 19th century was a revision of mechanics, and the idea of kinematics and dynamics grow up in that period. And so step 1 was kinematics, according to Cauchy or Ampere, and step 2 was dynamics. That means among all possible, kinematically possible histories, given a choice of what there is, that means particles, field, whatever, then the dynamics select the one. So it's not such a natural step. And about, this was one comment. Another comment I wanted to, so for me it's not so unnatural. The inertness, I mean, you quoted another thing that according to matter density, these are sort of, is really inert, no? You made the point of inertness. Okay, for me it's not a big problem. And for other people too, and for Ghirardi, I mean, Ghirardi came independently, basically, to this idea. I mean, we found, and we worked with him, but somehow he came to, he saw some problems in the option that you favor, and the option has to do, the problem has to do with the scale dependence of the ontology, how big is the object, the lack of additivity. So there are reasons to go the other way. I mean, that's what I think. I mean, but I mean, you do really. I mean, I like the presentation. You fairly show the pro and the cons of both.
Thank you.
Sorry, I should not intervene, but you're too much agreeing now, and I'm getting lost of what's going on here. Okay, so if you have a way,
If
It's important that both of them have drawbacks and favor. I mean, that's why I say it's the opposite of left. Both options have something in favor and some drawbacks.
Yeah,
For me, one of the options that has more in favor is the one that I like. I mean, the one, for me, the other one, the scale dependence, all this stuff, is going against the spirit of local beables introduced by Bell. I should remember that Bell introduced the flashes. I mean, it was not us that introduced the flashes.
I mean,
which I didn't even mention. Yes.
so,
Yeah.
No, just briefly, if you have a wave function only in your ontology,
Yes.
the wave function is not anything on normal physical space, on the Newtonian space.
Okay. Yeah.
So you have something more. I mean, I take the game to be that you need something more than the wave function. And now, to translate in my terminology, the space could be the primitive ontology, and you could have points or regions of space as your primitive ontology, and the wave function gives you the dynamics of them. That's not, I mean...
Yeah, so... Yeah,
there's no mysterious meta stuff or essence beyond space. Of course not.
Okay, yeah, so... thank you for that comment. And that... where's my... Okay, yeah, so here, yeah. Yeah, so... yeah, so here's the idea, and this I think also relates to a question that James asked of somebody: where does the wave function live? So, I really think the idea is you start with when you construct the quantum theory, you always start with a background space-time. Let it be Galilean space-time or Newtonian space-time, right?
Then you have more the wave function.
I should have said it explicitly. It was definitely implicit like this. We're identifying, so I mean, think of the way, think of how you construct the quantum field theory. So you start with Minkowski space-time, right? You associate with regions of space-time certain observables and things like that. There is this background space-time, and then a quantum state is an assignment, is a functional on that. So yeah, so now it is true that, okay, Nathan has a comment. Now it's true, so now to get a full quantum state, obviously you can't just take assign expectations values to observables in here and observables here. You need to have the pairwise coincidences and the triple coincidences up as far as the particular state goes. And but that doesn't mean that. And so for an n particle state, I have to have to get the whole thing, I have to have the all the n-fold coincidences at various places. But that doesn't mean that somehow or another the quantum state lives in this some kind of mysterious 3n dimensional space, because really, what I'm evaluating is expectation values at n tuples of the space that I started with. Yeah.
So now there is left and root and left.
Yeah.
Okay.
Yeah.
Well, I'll be very brief.
Yes.
I'm so glad you put this slide up first, and it's both relevant to what you, and so it's relevant. I was going to complain about this slide anyway.
Okay,
because,
complain.
Right. So in my experience,
Yes.
sometimes 2 comes before 1, and then as an example. Right?
Okay.
As an example, sometimes you have this problem like spin, which has no natural space-time background, and in fact, you want to try to, or maybe you're talking about color, or maybe you're talking about the multiplets of particle physics, right? It's not clear that there is an underlying space-time background, that you're identifying a system of interest. It sometimes 2 comes before 1.
Okay. Okay, I will accept that amendment.
Can I?
Exactly about this. I think you don't.
Could I ask my question, please? Yeah. So my concern is related to Nathan's, and I mean, how to make a quantum theory. I just would like to caution that maybe, if we're going to talk about how to make a quantum theory, we might want to go back and look at history. And there are many different ways that quantum theory was arrived at. One of them was Heisenberg trying to figure out where spectra were coming from and constructing his laundry lists. And nothing about his matrix mechanics had anything to do with assuming a space-time background. I mean, we all think we live in a space-time container, so that may seem natural, but what we have is different possible observables. We can define some are energy and momentum, and others are coordinate type of observables. So I just would caution about smuggling in an ontology while we're talking about how to make quantum theory.
Okay. Except, can I make a comment though? So Heisenberg, the 1925 paper, what he is interested is in the spectra of atoms and things like that, but they're actually you do have the step 1. Like if I'm if I've got some sample of hydrogen in my spectrometer, I think it's located in a particular region of space. And also, he was associating with the electrons things, dynamical variables P's and Q's, and then imposing the eventually and then finding himself representing those by what he later realized were matrices. And so I think that what Heisenberg is doing there isn't actually that far from the sort of picture I'm talking about.
I would just distinguish between phenomena, which are, as you said, located systems of interest, and an underlying ontology. So I wouldn't make that distinction.
What Michael said, too much agreement made me worry. Maybe,
Okay.
maybe I misunderstood you, because for me it's obvious that also in option 1 you add something to the wave function. Because observables are observables is what is arising in a measurement. But then at a certain point you declare that certain things that you construct in a certain way are real, are beables. So for me it was obvious that also option 1, you add stuff to the wave function. And that's why there was the agreement. I say, so you present two way. But if you leave out this and you say, no, I just look at observable, then there is, then there's a different story. Then there's, these are not observables, they're beables.
I meant, okay. I meant option 1 being you aren't adding additional ontology above the wave function. What you're doing is extending the eigenstate eigenvalue link, which was always part of what it meant to be. Without an association of operators with observables or dynamic quantities or something like that, you don't have a quantum state in the first place. If I just say I have a Hilbert space and I have a vector in a Hilbert space, there's nothing physical about that because every vector in a infinite dimensional Hilbert space is just like any other one in terms of the intrinsic properties of the Hilbert space. To make a physical theory, you need to associate subspaces of that Hilbert space with certain dynamical properties or operators certain dynamical properties, and that gives physical significance to the vectors or density matrices as physical states. Now, the usual interpretive link is the eigenstate eigenvalue link, and I'm not, when something is in an eigenstate of energy, the energy is real, and that's a fact about the quantum state. It's not ontology over above the quantum state. And I was taking option 1 to be just an extension of that interpretive property by an epsilon.
But still is an epsilon, it's not 0.
Yeah, right. Yes, exactly.
I think
Right.
I mean, the position is clear, and it's clear there's agreement, and
Yeah.
agreement ends. So thank you
Thank
very
you.
much again.